Thanks so much, Zeki, and thanks again for the invitation. It's really good to be here and talking to the wider quantum community about my work. So as Zeki mentioned, I am the Space Quantum Technologies Deputy Lead at the space engineering company situated in Glasgow in Scotland in the UK called Craft Prospect. So one of the interesting things about Glasgow is that this is actually one of the biggest CubeSat capitals in the world. Outside of California, the most number of CubeSats are situated in Glasgow, and the most number of CubeSats are manufactured in Glasgow, which is super interesting. But my journey to coming to CubeSats and bringing quantum into CubeSats and the space industry is slightly, it went a long way. So it went through quantum gravity and black holes and other kinds of quantum stuff, and then I came to satellites. So I'll talk about it in a bit. Apart from my academic work, I am also an equality, diversity, and inclusion consultant for various companies around the world, where I bring in the knowledge of causality. For example, like you're trying to build diverse and inclusive communities, which are super important because it has been shown that diversity and innovation go hand in hand. And also it's just a decent thing to do, right? But then we often do not use evidence-based approaches to build those communities. And so while we might have a very good motivation to bring in diversity and inclusion and work something for the wider community, we often end up having the opposite results. So that's where I come in with my expertise as well. And currently I'm in the Quantum India board, as well as one of the founding members of the New Voices in Space working group of the Scottish Space Leadership Council, which basically looks at diversity, inclusion, as well as innovation in the Scottish, as well as the wider UK space community and the UK quantum community. Right, so let me dive into my journey of gravity, first of all. So my journey, like everybody else's in gravity, basically started in school. A lot of us must remember that in high school, we basically learned about Newtonian gravity, right? So what was Newtonian gravity? Newtonian gravity said that gravity is basically a force between big objects or any two objects. So if we think of the system of our Earth and the moon going around it, then basically gravity is more like a spoke that exists between the moon and the Earth, and the moon basically goes around the Earth because it's being held by gravity to Earth. Now, this was super good. Like Newton's gravity theory was very successful. We could predict lots and lots of experimental observations that we saw in nature, and we could corroborate those predictions with experimental observations as well. But at some points around when Riemann and Einstein came into play, and even before that, around 63s, when astronomers started looking at the sky and actually making observations about how planets went around the sun, they figured out that Mercury actually had a slightly different way of going around the sun as opposed to other planets. And this they could not predict, however much they tried using Newtonian gravity. And this was one of the very first hints into the fact that there was something more beyond Newton gravity. And that's around the same time that people were starting to ask the question of, hey, what is space and time? Is space and time like a static thing? Is it a background upon which all of us are standing? Or is it something deeper? Now, during that time, when Riemann and Einstein came into play, so you'll also see that mathematics and physics often go hand in hand because mathematics provides physics and language. There was innovation in mathematics about Riemannian geometry, and that's what helped Einstein theorize that maybe we are wrong about gravity. Maybe gravity is not just a force, but maybe gravity is an actual geometry of space-time. What does it mean when I say gravity is an actual geometry of space-time, right? So if you can look at this animation on the screen, basically what Einstein was trying to tell us that anything which has a big mass and which has any kind of energy would bend the space-time around it towards object. So if you think about the Earth and the moon picture again, so in Newton's picture, the Earth and the moon were connected by a spoke. But what happens in Einstein's picture is that he's saying the Earth is there, it is bending the space around it, the space is creating a path, and the moon is basically just falling down that particular path. And this picture of general relativity is our most widely accepted theory of gravity today. And it has withstood a lot of experimental evidence. All of its predictions are still being validated. For example, we discovered gravitational waves. Recently, we also discovered that black holes exist. We have already taken a picture of a black hole. So general relativity started predicting that, okay, there are these massive objects called black holes, which exist in certain points in the space and time. And basically, which means that these are holes ripped through the curvature of space and time. But what it could not predict was that what actually happens inside those black holes, right? Now, at the same time, the other forces of the universe, like you have the weak nuclear force, you have the strong nuclear force, you have electromagnetic force, all of these forces started off as, so electromagnetism, for example, started off as a classical force, which Maxwell theorized. But then there was a quantum completion of that force. All of these other forces are understood that they are quantum phenomena, and we can understand them by using the theory known as quantum mechanics. Now, this was great because we could unify electricity and magnetism. We could basically, our whole world is quantum now because everywhere we use electricity. And if, half the time I joke that if people had asked Maxwell in his, application that, hey, you're doing some very theoretical work, why should we fund you? Because does this have real world applications? Now, he might not have said that he might have said that he doesn't know what real world applications his electromagnetism theory would have or quantum mechanics would have, but they do. Our whole world is quantum today. We are an electric world. We are lighted up, right? We use photons, we use electrons. Now, the problem was that nature, as we know it, is continuous. You would expect that a theory which works at particular scales should also continuously have a completion at other scales. So this created some confusion because every other force had a quantum completion, but gravity, general relativity, for some reason, we're still struggling to find what the quantum completion is. And this is what's known as quantum gravity, because we're sure that to understand what happens inside of black holes, to understand what happens at Planck scales, we really need to understand quantum gravity. There are many different theories of quantum gravity, which I'll come to in some time. We need to understand what the structure of space and time is by understanding how atoms and everything come together, which again, the standard model of particle physics does very well. And we also basically need to start looking at what kind of experiments we can actually do once we have a theory of quantum gravity. So my academics journey basically started with the institute known as IISER Kolkata in India. It's the Indian Institute of Science, Education and Research. I got very lucky because these are one of the topmost theoretical research institute, not just theoretical, research institutes in India. And they offered a lot of interdisciplinary research opportunities. They also mandated that as a KVPY fellow, which is the Young Scientist Fellowship that people who went into those universities had to kind of take a test, and then you get a scholarship, and then you can go in. So the way it was structured was that every year we kind of had to do a summer project and a research project and write a report. And then that means that then we will get our next year's scholarship. So yes, everybody needed money. So we did a lot of research projects. And one of the very hands-on research project that I got to do was actually at LIGO in Caltech. So I was part of the gravitational waves team working on the prototype gravitational wave detector in one of the topmost labs in the world. And that instills in you a bit of research culture. It also gave me a lot of hands-on expertise in optics and photonics and instrumentation and electronics at the same time. I also dabbled around in biophotonics in a lab in IISER again. We were working on how do we use light particles, scattering of light, to detect cancer. And there is a paper in my profile if people want to go look it up. There's some very interesting work going on in that field as well. After doing a lot of work in quantum optics for the first 3-4 years in experimentation, actually, I also did a few work in quantum computing and understanding what are the early days problems in quantum computers were, what are the interesting problems in quantum information. I was really interested in applying quantum information to black holes at that time because black holes can provide a really interesting laboratory to understand if we can actually understand the whole world, whole of space and time as made of information. as quantum information, for example. Later on, I realized that I wanted to shift onto theory a little bit, so I did my thesis in various theories of quantum gravity. In ISA Kolkata, I did my thesis in understanding loop quantum gravity, and especially a toy model of loop quantum gravity known as um, um, it, it was basically a mathematical theory which dealt with how do we understand what happens inside of black holes using quantum field theory. And then I went to Perimeter Institute of Theoretical Physics, where I got accepted in their PSI program, which is often said as the boot camp for physicists. And it is actually a boot camp because it's super hard. And by the end of that year, we were all just really done with physics and needed a bit of a break. But then the stuff that we got to study, and my thesis was again on string theory, especially a reformulation of string theory in the phase space. And I don't want to go into details of all of these because these are super technical and would probably sound like I'm speaking nonsense. But it also gave me a lot of breadth and depth into the fundamentals of quantum mechanics. I did a lot of outreach at the same time, talking about what we do to university students and to the wider community, which always gives you a good idea of where the divide between the academic knowledge and the general public's knowledge is. And the more we do these kind of outreaches, we can disseminate more information, which would imply that knowledge always increases when shared. So that's super good. I then moved, like Canada was super cold for me. I was supposed to stay on to do my PhD, but I decided to move on to slightly less colder places. And I already have a invitation from the University of Sussex. So I went there to work on quantum gravity during my PhD, as well as on particle physics. This is some picture of like some of us with Roger Penrose, who was the recipient of last year's Nobel Prize in Blackholes. That was a nicer. This is a picture of me with Stephen Hawking. I was really lucky again to meet him because we worked in the same kind of fields, and so you kind of cross paths at conferences, and got super lucky to get a picture with him as well. This was just a year before he passed away, so which was quite sad. But the reason I put on these pictures is that when you meet people who do really cutting edge work, then you actually get really inspired and use them as your role models. And then I got, like during my PhD, basically I started working on particular theories of quantum gravity. So I tried to understand what would happen inside black holes if I used effective field theories of quantum gravity. And then how do we actually use gravitational waves to detect whether these theories are correct? So we theorized that in addition to the waves that current LIGO is detecting, the gravitational waves, if there is quantum gravity inside of black holes and that theory is correct, then we should be able to see two different modes of gravitational waves. Now, this is quite an interesting discovery. We were all super excited. But again, as always, we kind of have to wait for technology and engineering to catch up to where theory is so that we can validate our theoretical predictions as experimental findings. And probably I'll not get to see whether these findings are going to be validated before I die. But that's all right, because we're all standing on each other's shoulders anyway, right? All right, so basically during my PhD, I found out that black holes, they provide a very interesting laboratory in space to study the interplay of long distance phenomena such as GR, general relativity, like I was saying, as well as very short distance phenomena, which are also called as infrared phenomena. We know that classical GR breaks down at the event horizon of black holes. We also know that quite a few different theories of quantum gravity actually work, like they are pretty solid theories of quantum gravity. However, we are unable to unify them with other forces of quantum gravity, other forces of nature like the weak nuclear force, the strong nuclear force, and so on, which is important to understanding how the world works all continuously and uniformly. Now, to understand all of these much better, we need to kind of dive into the fundamentals of quantum mechanics. And there are so many open questions in quantum mechanics right now. What do you mean by a measurement? What do you mean by an observation? How do you define an observer? And I'm not going to go into a lot of technical details because, as Ziki said, these kind of talks are more about disseminating what are the cutting edge things that are happening, as opposed to going into the mathematical details of it. But I'm giving you all of my journey, so that you understand how everything is kind of linked to each other. So you might take one subject in college and undergrad, and then you might go on to study something else in your PhD, and then you can take that skill and knowledge and then apply it somewhere else. And that's just very normal transferable skills in research. And you shouldn't be feeling like you're held back by a particular choice of subject. So this was super exciting. Last year's Nobel Prize went to Penrose, Genzel, and Gez for their work on black holes. And so it felt really exciting to all of us who were working in the field. And over the years, like during my undergraduate, I was only one of two women in physics in my batch of 100 kids. And I think that came with its own challenges. And a lot of people don't realize how challenging it is to work as a minority gender in a particular university where you're at, because it gatekeeps a lot of knowledge from you. And I think a lot of the problems that we find in when there are gender skewed demographics in particular universities is that, first of all, there's a lot of harassment which does not go picked up as harassment. I didn't even know half the things that happened was harassment. You often do not find a lot of female role models, and the few female role models that are there get mocked by other students, especially male students, and you tend to also inculcate all of those toxic masculinity and misogynist tendencies into yourself. And once I went into a slightly more gender equal groups, I started working on myself to get rid of all the weird misogynistic tendencies that I had picked up over the years. I also obviously I got lucky. I had access to a whole host of role models during my journey from India to Canada to the US to UK. And it's very good to take opportunities where they come, because you're going to go and get exposed to many different kinds of people. It's very important to see that physicists can look like anybody and any gender, any sexual orientation, any kind of disabilities. Whatever you think is holding you back actually should not hold you back, because other people and society and people who are making policy should be thinking about these things carefully. And if you start asking about this is how I think we think should be done, so that it makes it easier for me, then that's the starting point. So always speak up, and always try and keep a mind open about your colleagues. For example, like, are they facing some problems that you're not aware of? Is there some disability which is invisible, and they are just trying to make more of an effort during their day to produce the same amount of work that you do, for example? So these are very small, subtle points, but they go a long way, because fighting with invisible disabilities, as well as just gender discrimination, takes a lot of energy and effort, which could have otherwise gone into actually doing physics. Okay. Next, let's basically start into how I transitioned into working on like fundamentals of quantum mechanics, and then coming to the satellite and space industry. So when I was finishing my PhD, I was very interested to continue working in research, but I was also interested to take my knowledge and apply it into some other industry, for example, because I felt that was like a good combination of my strengths. So what is quantum, right? When we say quantum, there's so much hype about quantum. What exactly is the word quantum? A lot of people actually use the word quantum wrong. Quantum means the study of the extremely small, but extremely small, much less than 10 to the power minus 15 meter, which is the size of an atom. And what are quantum technologies? Quantum technologies are technologies which manipulate quantum particles such as single photons and electrons, and so that we can use them for our benefits, right? And it's incredible that we already have technologies which can manipulate such small particles, right? Now, before I go into talking about how do I take quantum into the space industry and satellites, I want to talk to you a little bit about what are CubeSats. The particular kind of satellites I currently work on are called CubeSats. They are a type of small satellites or nanosatellites, which are known as CubeSats because they are basically cubes stacked on top of one another. So if you can see on the right-hand corner here, this is a 1U unit of a CubeSat. CubeSats were first built or conceptualized in Stanford by a couple of researchers because they thought that students who were working in the satellite industry or who were studying in the satellite industry kind of need to get access to smaller satellites that they can build and have a hands-on experience with. So CubeSats started off as university projects. Again, which is super interesting because university projects can go into becoming something that is used in the topmost space organizations in the world, which is great. So these 1U CubeSats are basically 10 centimeter times 10 centimeter times 10 centimeters, so 10 centimeter cubed cubes. And then you would be able to stack them on top of each other. And then so a 6U CubeSat looks like that, and a 12U CubeSat looks like that, and they're all pretty small. This is a particularly big loaf of bread that I'm showing on the right-hand side. CubeSats in real life kind of look like a skeleton. These are basically the buses inside which you can put as many interesting technologies you want to and send them into space. There would be solar panels on the outside, there will be some thrusters, there would be some kind of stabilizers that they would have, motors that will stabilize them from rolling over all the time in orbit and so on. But basically they are a metal cage, right? Now, what I currently work on is early stage quantum technologies. And one of the biggest applications of early stage quantum technologies at the moment is in cryptography. So as everybody knows, today's world, we are just using loads and loads and loads and loads of data. In the remote COVID world, for example, we're just doing everything virtually. We are storing so much amount of data in the cloud, and we have a lot of internet connections. And our world is basically a mass of connections. Now, with great power comes great responsibility. With great data comes great responsibility. This information needs a lot of encryption. We need to be protected because, for example, if you're giving your data to hospitals, you want to ensure that somebody else is not taking your data and then using that for nefarious purposes. You want to be sure that banks are not leaking your data again. You want to be sure that when you're doing an ATM transaction or a online banking transaction, nobody else is eavesdropping on your OTPs and then using that to use your money, and so on and so forth. And we have seen a lot of cyber attacks happen more and more and more right now. And the way we do the encryption of our current data is by public key cryptography, which is something which is very widely used. And this uses mathematical complexity to ensure encryption for elongated times. When I say mathematical complexity, what do I mean? Basically, people figured out that if you take two really big prime numbers and then multiply them together, you have the product of these two really big prime numbers. You use that as some form of a key. Now, it takes classical computers more than the lifetime of the universe, in some cases, to factorize that big product at the end and find out which two prime numbers were the factors. And unless you can do that, you wouldn't be able to hack these systems. That's a very simplistical definition, but hopefully that gives you an idea. Now, the problem is today we actually have a threat to this kind of cryptography. Quantum computers are now on the horizon. And since all of you are in the quantum computing community, you know a lot more about quantum computers, hopefully, or at least the bare basics of what quantum computers are. So quantum computers basically use quantum states again to perform calculations much faster than classical computers, because in classical computers, you just have access to 0 and 1, which are 2 bits. But then in quantum computers, you'll have access to multiple qubits. Excuse me. Yeah, so with the increase in computing power and with quantum computing, it will be really easy to break even the toughest classical encryption mechanisms. There are some very good blogs nowadays which tell you exactly how much time today's quantum computers are going to take. Today's quantum computers do not have as many stable qubits as we would like to make these, to break these encryptions, but in the next 5 to 10 years, we will definitely get there. Also, even if we don't get there in the next 3 years, for example, people would still be downloading the information that we have unless we protect them in a different way. And once this information is downloaded, they can store it. And when they have access to a commercial quantum computer, they can take that information and break the encryption on them and get access to our data. The global cybersecurity market is currently worth $173 billion in 2020. This is growing to $270 billion by 2026. And 77% of cybersecurity spending will be for externally managed security services. And also in-house cybersecurity functions expected to grow 7.2% each year to 2026. Basically, this is to say that there is a big cybercrime syndicate, and the value is only increasing day by day. And so there is a very real threat to data. Now, how do we actually ensure that we can protect our data against quantum computers? It seems like a big challenge, right? So in normal computers, in normal encryption, what you would do is you would take some dedicated hardware, you would find a clever algorithm, you would take a quantum computer, you would or you would wait a few years and wait for a quantum computer, and then you would break those encryptions. But what we can do is we can actually use quantum, this word that we keep using again and again. We can use quantum to actually encrypt our data instead of just using it to decrypt our data. Now, quantum computers can obviously be used for multiple different purposes, and cybercrime is just one of them. But yeah, we need to ensure that we can use quantum as well to do some new and innovative cryptography. And it's good because when you have one kind of technology coming on the market like quantum computers, it often pushes the innovation in other fields. And that's what we are seeing right now. So how do we use quantum to do cryptography? What is quantum cryptography? So quantum cryptography basically means that we will use single quantum particles like photons and their quantum states to encode some information in them, right? So in Craft Prospect, the particular kind of QKD that we are hoping to achieve using a satellite is called the BB84 single photon QKD. What we are going to be doing is taking a photon. We will polarize the photon. Now, photons are made up of two different main polarization states. They can be either left polarized or right circularly polarized, and we can also break those down into different bases. We can make them vertically polarized or horizontally polarized. We can make them anti-diagonally polarized or diagonally polarized. And what we can do is we can say that, let's say the vertical polarization is 0 and the horizontal polarization state is 1. And this is how you would encode information in a polarization of a photon. And the polarization of a photon is a quantum state. There are other quantum states of photons. You can use phase to encode information. You can use spin to encode information, lots of other things, right? So basically, what is quantum key distribution? It's a quantum cryptography protocol which uses the inherent quantum properties of photons to make encryption secure, even future-proof and secure from quantum computers. I'll explain that in a bit. We can use either single photons or encode information in their polarization states or use entangled photons. So a few different places in the world are using entangled photon sources. We are using single photon sources. We have various different quantum key distribution protocols which have their own security proofs, and you might choose one over the other. Currently, there are actually many commercial QKD systems out there already. Now, simplistically, what exactly is a QKD system, right? The QKD system looks like this. You have an Alice and a Bob. Alice and a Bob are just normal, names that we use in the quantum community. Alice is the transmitter, the sender. So let's say I am Alice and all of you listening to me are Bobs. So if I want to send you a key that we can use for future secure communication, I will have a transmitter. I will hold the transmitter in my hand. You will have a receiver on your side. I will prepare a photon in a particular quantum state. Then I will shoot those photons over to you through either we will be connected by a fiber optic cable, or I will just send the photons through the atmosphere and you would just receive it on your receiver. Now, when you receive the photons on your side, Bob's side, then you would measure the photons. You will measure the quantum state of the photon. Measurement of a quantum state causes this collapse. And so you would be able to find out what exactly did I encode? What information did I exactly encode? And then you would be able to distill that information into a key, which both of us will be able to use in the future. Now, a problem with this is that if we want to do it terrestrially, photons are really, really, really tiny particles, as I mentioned. Now, if they are traveling through fiber optics or they are traveling through free space, there would be a lot of losses and they would not be able to travel more than 500 to 600 kilometers maximum after using repeaters. And quantum repeaters can be a very interesting solution, but we haven't yet seen any practical usage of them, which do not make me have a good confidence in the fact in that we can actually use those quantum repeaters to make long distance quantum communication. And why are we interested in long distance quantum communication? For example, if I'm in the UK and I want to talk to somebody in the US or Canada, then we are not connected by less than 500 kilometers. So I would need to send photons through more than 1,000, 2,500 kilometers, and that's a long way. So if we want to connect the globe securely, because in order to make sure that we are all, in order to make sure that I am secure against cyber attacks, I need to make sure that all my connections are secure against cyber attacks, and all my connections are all over the world, and all of us are connected all over the world. So all of that network has to be upgraded simultaneously. So in order to do a global coverage, in order to say that I want to send something to someone in the Canada, I would not be able to just do it using terrestrial QKD. This is where space will come in, right? So space basically helps us to reduce this distance by, let's say that I will say that, okay, I will set up a ground station here. And you guys, some of you might be situated in Canada, for example, you're going to be setting up your ground station in Canada, right? So we come to an agreement and we send up a satellite together. This satellite can go into a LEO orbit, which is around 500 kilometers above Earth. So when the satellite first goes on top of my ground station and has a line of sight communication possible, it will open a quantum channel, very Star Wars, right? It'll open a quantum channel and it will send down some photons. And I will be able to receive those photons and I will be able to distill a key. When the satellite then goes in its orbit and then goes over the next ground station, it can then open a quantum channel over that other ground station, which is situated in some other country, which I wouldn't be able to connect to using terrestrial QKD. So again, the distance between the ground stations and the satellite is going to be a maximum of 500 to 600 kilometers in LEO. And specifically, the losses are going to be even lower because most of the time, the photons are going to be traveling through free space as opposed to atmosphere. The last 10 kilometers is often atmosphere. So as opposed to losses, because photons travel all the time through atmosphere, this is going to be the vacuum of space, plays a major role here. But in order to do that, we need to be able to send up multiple different CubeSats and multiple different orbits, which connect multiple different ground stations around the world. And that is why we are placing such a big emphasis on small satellites as opposed to conventional satellites, because conventional satellites are really big, they're super heavy, they're super expensive, they need a big team, they need like space organizations like ISRO or NASA to build them and send them up and deploy them. Now, small satellites do not need as big teams, and that's why startups like us can actually work on small satellites. They are super easy. We often use commercial off-the-shelf components because we just buy stuff, off the shelf. We go online, we look at what kind of sensors are available. We just buy them and we customize them in-house, but with minimal effort. And also, most small satellites missions kind of cost around £1 to £2 million, which are much, much, much less than what bigger satellites usually cost. One of the first quantum key distribution demonstrations was actually done on a bigger conventional satellite by China. In the MICEUS satellite, it's actually the only country till now which has done QKD demonstration. Again, the rest of the world is kind of trying to catch up with China at the moment. And there are quite a lot of small satellite missions. Well, when I say lot, I basically mean 3 or 4, because that's the number that means a lot in the space industry at the moment. So there's quite a few small satellite missions that are being planned around the world, and we aim to showcase different kinds of QKD. What my job was basically demonstrating QKD in the lab first, and then try to miniaturize a payload. So when we work with universities in Bristol, in Strathclyde here, so this slide basically shows that if we want to go to a quantum internet, then this would require a big constellation of satellites around the Earth. And smaller satellites, they cost less, they are easier and faster to deploy, and so they have more risk appetite. So we can be more ambitious in our plans of what we want to demonstrate, right? I'll come into the making of a CubeSat QKD payload in a little bit. But I also want to just talk to you that what do we really do? What the challenge lies in taking a really big optics table in a university lab and then miniaturizing it into a really small payload that fits on the top of your palms. So the making of a CubeSat QKD payload has like multiple different layers and multiple different steps that need to go through. You will need to think about what's the computer on board, which is going to be sending commands to do the actual QKD. You will need to think about what is the software I want to be using, what is the protocol, what is the UI system, for example, am I using Linux, am I using a Windows module, what exactly am I using? You'll have to use a lot of embedded systems. You'll have to look at the electrical and hardware connections. You'll have to then, at the end, look at the optical systems, which are the lasers, the LEDs, the mirrors, the telescopes. And all of these are big, and they all have to be kind of innovatively space cut out so that everything fits on the top of my palm. And I'll be showing you the picture of like a little payload that we have actually built already and are offering it as a product. Now, in order to put quantum in a CubeSat, some of the things that we do are, first, we have like a neural network and imaging system. So this is where my background in AI comes into play. We have an AI team in-house, and we work with researchers at universities all the time. So you have a particular neural network, which first of all looks ahead using a camera. It goes over particular ground stations, but before we reach a particular ground station, it looks ahead and takes pictures to then go back and process those pictures on board while in orbit and see whether there's a cloud cover on top of a particular ground station. If there is cloud cover, then we would not be able to do efficient QKD. The photons would not be able to go through that much matter, basically. There would be a lot of loss, which is what we're trying to minimize using a satellite in the first place. So we wouldn't be able to do QKD, and that will be expensive because that means that we are losing one orbital pass and we are just waiting another 24 hours to send down a few keys to our customer or to anybody who needs it, really. I'm just using the fancy word customer as a placeholder. So this is where the neural networks come into play. They will make smart decisions. They see the clouds, they will do image classification, find out about the clouds. Then they will say, hey, this particular ground station is covered by clouds. So let's not try and do QKD in this particular ground station, but let me go and look around this area and see whether we have other ground stations who want keys. So once the neural network and the imaging system combined together finds a ground station which is not covered by clouds, it then commands the secure computer to say, hello, we found some ground station which does not have clouds, so we have acceptable losses. Why don't you go and start QKD? So the secure computer basically then goes through the electronics layers to do a bunch of commands. Then we actually interface with a quantum random number generator. Now, this quantum random number generator is another quantum technology. And the reason we use this is to generate true random numbers. So in any kind of cryptography, be it quantum cryptography or classical cryptography, you need good random numbers. And a lot of the cyber attacks happen because the entropy of the random number generator that people use, the randomness source that people use, is very low. So these, with quantum random number generators, again, like a few different quantum random number generators are found commercially at the moment, and then there is very rapid development happening in that field. So they produce true random numbers, and then those random numbers would, again, drive the laser drivers. They will figure out what kind of intensity the lasers will emit, for example, and then you would go into QKD. The lasers will fire laser pulses. They will go through all the optical paths with optics, lenses, collimators, mirrors, so on, telescopes. And then finally, you'll have the quantum channel, which takes the photons down into the Earth to the ground station. Now, basically, the upcoming mission that we have at Craft is called ROCKS. It's supposed to be launched next year. It's called Responsive Operations for Key Services. And responsive operations basically stands for the AI and automation part, and key services for the QKD part. So basically, ROCKS will be providing keys at a 500 kilometers LEO orbit using quantum channel, and then it will also be using an RF channel for doing some of the post-processing that needs to happen in QKD. And also we will be using we are working with our partners at the University of Bristol to build a mobile ground station. So we would be able to just basically put it at the back of a van and then carry it around, because a lot of you might know that in Scotland, we have a lot of rain. So there would be lots of clouds. So hopefully we'll be able to move them around to other parts in the UK where there will be not that many clouds. But at the same time, we already have our quantum source. So another thing that I wanted to say is we have built our own quantum source. So quantum source is basically a quantum tech that you build. Now, this can be either a single photon source, as I mentioned before, or an entangled photon source. There are other missions in the UK which are doing entangled photon QKD. So we decided to go for single photon QKD. But true single photon sources are very hard to make commercially. True single photons are just really hard to produce commercially and at a fast rate that we need. So most of the time what people use is something known as a weak coherent laser pulse source. So what that means is that you take lasers, you fire a lot of photons, but then you attenuate it down heavily by using a lot of ND filters or any kind of attenuators to make sure that every single pulse has one photon. Because if you have more than one photon, an adversary can actually look at you, can listen to you, and then take one photon midway and make some measurements. Now, I said all of this, but what is the biggest thing that QKD brings to the table? Because we use the quantum properties of these photons, when Bob, you guys, will measure the photon, basically you're altering the quantum state of the photons, right? If some other eavesdropper wants to basically intercept this transmission midway, then they would also have to measure the photon, and they would also alter the quantum state of that photon. So even if they kind of inject some other photon, preparing another quantum state, we will be able to calculate what are the errors in the photons that were sent and received. And if the error are above a certain threshold, then we'll always be able to tell that somebody was trying to listen in. Whether it was a quantum computer or whether it was like a normal person, it doesn't matter. We'll always find out. So that's what QKD is really good at. I had a few other nice animations just showing QKD. So you have like all the different polarization bases, which are represented by the different kinds of arrows. You have a QRNG, and then the QRNG fires off a random stream of polarization bases. Bob receives those bases through the quantum channel. He then changes them into like bit values 0 or 1. And then Alice and Bob basically compare over the classical channel what polarization bases they had used to prepare those particular quantum states. And then they compare, then there's a process known as key sifting, then there's error correction and parameter estimation. And then you have privacy amplification, which then make the secure key even more secure. And then finally you get a secure key, which you would be able to use in the future for secure communication. And the last stage of all of this is that after you actually build all of this, you'll have to evaluate them for security. Now, that again is like, there's a huge laundry list of going through what do you do to evaluate something for security. You first evaluate the security of the protocol. Now, there are multiple theoretical papers that are out there which give you the mathematical security of the protocols. Then you have to evaluate the security of side channels. Am I leaking something? Is there some either photon leakage or other electromagnetic leakage? Then you would have to look at a key management layer. You would have to, like, if you're providing these keys as a commercial service, then you would also need to make sure that you're deleting the keys at the right times, because otherwise they would be insecure after some time. You would not have a great level of trust in the fact that they have not been leaked. You also need to be authenticating the classical channel over which there's all the error correction and everything that happens. You need to evaluate the randomness of the QRNG. If the QRNG output is not random, you need to stop QKD, or you need to increase the randomness of the random numbers that you're using. You need to evaluate every single layer, the electronics layer, the optical layer, the secure computer, all the different links. You also need to think about what other kinds of security you need in space. Since we are also using a lot of commercial off-the-shelf components, we also need to think about what are the insecurities and insecurities basically which exist in those components, because nobody is building them for high security applications. And then we are using a lot of open source systems such as Linux. And so we also have to think about the security of these open source systems, and also making sure that we are upgrading the security with patches from time to time. Now, theoretically, work has matured. Technologically, we're doing a lot of us, like the whole world is actually doing all of this for the very first time. And so a lot of innovation is required. Quantum sources, manipulating single photons, long distance entanglement, teleportation, all of these have risks involved. We need to be miniaturizing electronics and devices. We need to be testing them for whether they are radiation hardy, because they are going to be working in the space environment where they will be exposed to a lot of radiation. We would have a lot of tiny instruments which might just break during launch. So we have to basically shake them hard before we do the launch to make sure that we are breaking everything that is going to break, and we are not sending stuff that we are not happy with. We also have to figure out how to fit everything inside a CubeSat, and that is done by our mechanical engineers on site. We also have lots of lasers, so we have to think about laser safety. We have to think about regulations in space, like what are the standards? Do people have security standards for QTD? And ETSI is an international organization which is coming up with those standards currently. So it's all in process. There are a lot of like moving parts which are happening together. Yeah, and this is exciting because this is a snapshot of the actual payload box that we are making on the right-hand side. And for scale, you can see that this is the CubeSat, the blue thing. And then this little box is basically the whole of the QKD payload box, which is going to go inside the CubeSat. And we would have another secure computer payload. We will have the neural network payload, and the CubeSat provider is also going to be adding on some star trackers as well. These are like some of the development boards that we are using to put all the embedded systems on. Before I finish, I also wanted to just point out that I already talked about MyCS, the Chinese mission. There are lots of other missions like Space, which is a UK-Singapore bilateral mission, which is using entangled photon source on board to showcase entangled source QKD. ROX is going to be demonstrating WCP source QKD. We are actually also collaborating with KeySat in Canada. We are providing them with our quantum source so that they would be able to also do both entangled source QKD as well as single photon QKD. I remember that there was also a German mission recently, which is also trying to demonstrate QKD. I'm not sure whether that's single photon or entangled photon. And I know that India also has plans to send up its own QKD missions, and probably we'll hear a lot of other missions coming up on the radar quite soon. So yeah, and this was mostly about my journey from black holes to quantum, and what do I work in quantum technologies at the moment. And I'm happy to take any questions. So thanks very much.
Thank you, Sonali. That was a great talk.